If you've ever taken a calculus-related course before, you've used this notation at least once. Of course, I'm talking about the limit notation. If you need a reminder of what it does, it's how we describe the expected end behavior of a function as it approaches a certain input value. And that's all the limit notation is. It doesn't carry any more meaning than that, and what's presented doesn't necessarily have to be true. For example, let's say that our f of x is the expression 2x plus 2, and that what we want to approach on the x-axis is 3. Then we state that as we approach 3, we expect the end behavior to be 7. Now, obviously, if you use basic algebra or plot the equation on the graph, you can immediately tell that this limit is just not true. But how can we prove that in a formal way? Well, let me introduce a nifty little definition to help set that right up. Introducing the Epsilon-delta definition of a limit. As you can see on screen, that's the formal definition, and you can pause the video if you want to read it all, but I have a way I like to think about it that helps conceptually. So, we define two variables, epsilon and delta, which indicate the tolerance of the inputs and outputs of a function. These tolerances help establish intervals that are meant to be infinitely small, meaning that epsilon and delta are values that must be able to continuously get smaller but never reach 0. And if the expected end behavior remains in that output interval, no matter how small it gets, then the limit is true. At least, that's the concept behind it. Now, let's take a look at an example of a valid limit and use this definition in combination with a mathematical proof. First, we should declare that for this proof, the value picked for epsilon must be a value greater than 0. Next, we have to find a value for delta that ties back to epsilon. Now, why is that? Well, conceptually, we want to make sure that any valid input between the delta interval results in a valid output. To find what delta should be, I think it would be wise to take a look back at the formal definition we had earlier. There, we'll find two inequalities that define intervals for both delta and epsilon. And we can see that the values and expressions that we declare for our limit can be placed right into those inequalities. So, let's start off with the epsilon inequality by plugging in the expression of our limit and subtracting it from our expected end behavior, which can be simplified into this. Now, let's look at what we can do for the delta inequality. We can see that a can be replaced with 1, since that's the point we're approaching, and we can also discard the greater than 0 part of the expression, since it's assumed to be true regardless of what we input for x. And looking back at what we have for the epsilon inequality, it looks like we can take away a common multiple, which leaves us with something oddly familiar, right? If we were to compare it directly against what we have for the delta inequality, you may notice that the only difference is that one side is multiplied by 3. So we can transform the inequality into this, which means that delta in relation to epsilon is in fact equal to epsilon divided by 3, proven by pure algebra. Since we're doing a proof, we have to ensure that by going through those steps, we can end up back where we started, which can simply be done by stating this. And that finishes the proof for us that our limit is in fact true. Now, do you remember that clearly incorrect limit I introduced earlier? Well, let's try to apply this definition and proof to that same expression. We'll start with the same steps we did with the previous problem, and we'll substitute our function and expected end behavior into the epsilon inequality. Let's also do the same for the delta inequality. You may already notice that we can't simplify the expression within the epsilon inequality, and even if we try, we won't end up getting closer to something like the delta inequality. So if we can't do that, then it's simple to say the limit expressed is just not true. Either way, we can't continue with the proof. Now, I would continue listing other problems with limits of quadratics, cubics, and what have you, but I have a limited amount of time. However, what I've described and what I've shown can be applied to other continuous intervals, with some variables being capped. With something like this, you may ask, when are you ever going to apply this definition, and how will this be useful? I'll be honest, I don't know. But what I do know is that this helps establish how we can solve limits and prove that what we say is ultimately true. Because limits are the backbone of calculus. They help define derivatives, and while I may not have gone too in depth with this video, I hope that what I've shown is another way to think about limits and how they operate. So, thank you for watching, and I hope that you have a good rest of your day.